Hello, testing. Yeah, let's start first because I think we have a lot of things to discuss. Okay, last time we talked about this set C here. If I given a topology, how do you find a basis, right? So how to find a basis? What's this C here? We take all the open set. Sorry, where's the screen? Okay, so how we find this C here? So we start with a topological space, meaning what? I have a set and then I know who are open. Yeah, I have a set, I know who are open. And then we take all the open set such that what? Such that for every open set in X, okay, at every point in the open set, we can find a C that contain the point X and is lie inside U. Okay, we find all the C that can do this. And then these are my basis elements. And then Sony asked this whether this thing is whether this set is so whether this set is unique or not. Unique in the sense that in the sense of cardinality. So is it like can you find so for each topology, right? Can you find how to say it's not that can you find is whether given a topology how to say given a topology this set will create the smallest basis. Yeah, will create a smaller basis. Okay. If you guys think about it, whether this set will produce the smallest basis for the topology. So you need to start with some topology to play with, and then try and find what basis, what C you will get. And yeah, right. So last time we discussed that this set here won't give you unique, will give you unique smaller set. Right. So let's say if you have one basis, okay, you could potentially get another basis, but they are different. Okay? Then in this case here, non-uniqueness will imply this is not the smallest one because you can just put them together, still satisfy this property. But we're going to see in a real example later, okay, that a topology will have, one topology will have different bases. And then in that case, you can match all the basis element together, still satisfy this property here, still form a basis. Okay, so that means this property here doesn't pick up the smallest basis. Okay, doesn't pick up the smallest basis. Does it make sense? Make sense or not? Okay. Okay. So let's do one lemma and then we will do one example. So last time we talked about whether a topology is finer than the other, right? And today we will link it with basis element. Okay, that B and B prime be basis for the topologies. So respectively on X. Then the following are equivalent. So then TFA. Okay. So first, if we say that T prime is finer than T, recall what does this mean? So T contain T prime or T prime contain T? T prime contains T. So this is what finer means. And second property is for every x in X such that for every b in B, okay, and if S is in B, then there exists a B prime, okay, the script B prime, such that X is in B prime and this B prime is in B. Okay, let's think about it. What does this mean here? So every point in X, okay, and every B, every basis element of B, such that this basis element contains X, you can find another basis element, okay, for another basis, a basis element for another basis, such that this basis element will contain X and contain B. Okay, meaning what? Meaning what? Basis element here contained in B. Yeah, this is open set, right? So it's like B is open in B prime. B is open in B prime. Okay, so we will show this. Um, we'll try and show this TFAE here. So let's try and prove it. Come to 2. So first we suppose that T prime contains T. Okay, so we want to produce the second statement here. So you need to fix some X and fix some B. Let's fix some point X and some basis element. Okay, such that this basis element contains X. So you want to find this B prime here from a new, from the other basis. Okay, B prime, script B prime. Can we do that? Can we do that? How do we find this B prime here? Where is B? Yeah? B belongs to who? B belongs to T because this T is generated by this basis here. But T is a subset of T prime, meaning what? B is open in T, is an open set in T. So if B is an open set in T, we say B is open in T, okay? B is open in T, but T, everything in T is in T prime. So meaning B is open in T prime. It's an open set in T prime, right? Okay. But T prime is generated by this B prime, right? So this means what? Since B is in T prime and T prime is generated by B prime. So if you are a topology generated by a basis, it means that there exists a B prime in B, script B prime, such that X is in B prime, which is in B. Yeah. This is what it means to be open in a topology generated by basis. Okay. 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 You can use some basis element to cover your point. Okay. How about 2 to 1? Okay. Suppose the second condition hold, you want to show that contain T. Okay. So meaning every open set in T, you need to show that it is an open set in T prime. So just take one open set in, an open set in. Okay, you want to show that, so we need to show that U is open in T prime. Okay. So how do we do this? Means what? T is a topology generated by a basis. Last time, what did we show about this kind of topology? The opens, how does the open set inside T looks like? So let's go back a bit. How do we describe the open set, the topology that generated by the open set? The basis element. So if we have a X, a set S, and a basis for topology T, okay, then my topology are the collection of all unions of basis element. Okay, so all the open set can be written as union of basis elements. Okay, so from here, okay, from previous lemma, U is equals to the union of alpha of B alpha. Okay, where B alpha is in T. So what's good thing about this? This means what? If I want to take X is in U, this implies what? X is in B alpha. For some B alpha in. Make sense? Okay. To show that U is open, to show that U is open in T prime. Okay. What do we get here? By part 2, what do we have? For every X in X, if you have a B that contain X, then I can find a B prime. Okay, then I can find a B prime. So I can find a B prime in script B prime such that X is in B prime, and this B prime here is in B alpha. Okay, but if you are in one of the B alpha, right, this means what? This is in the union of B alpha, which is equals to U. Okay, so this means what? You have a B prime in U. So meaning U is open in T prime because you found a basis element in T prime which contain X and contain in U. Yeah, no. Okay. Okay. So when you want to talk about final, right, you can do what we did last time if you have control of all the open set. Otherwise, you can use the basis to check. Okay, otherwise you can use the basis to check. If this property holds on basis, you see the okay. If this properties hold on basis, then you can say that one topology is finer than the other. Does it make sense? Does it make sense or not? Any question? Okay, I give you one example. Maybe you can ask later. So let's look at one example here. Okay. Let's consider the Euclidean topology. Euclidean R2 topology. R2 Euclidean topology. Okay, let's put like this. R2 Euclidean. Okay. So you can prove that there are two kind of bases you can pick. Okay. So you can consider B to be the set of open ball. So let's do it like this. So all open ball, or you can pick all rectangle, open rectangle. So, so you can pick all open rectangle. You can try and show that. So you can try and prove that they form basis for R2. Okay, with the Euclidean topology here. Okay, so to check for basis, what do you need to check? What's the two property? First property, for every point in the matrix space, in the topological space, you have a basis element that cover that X. Okay, this is the first property. Second property, if your point lies inside the intersection of two bases, you can find another basis element that contains that point and also lies inside the intersection. Okay, so you check whether this is true or not. Is it true for you? Can you quickly see? Okay, and then you check that this will give you back the Euclidean topology. Okay, show that the T generated by B prime and B is really equals to the Euclidean topology you have. Okay, but using this two property, right? Using this two equivalent statement here, we can prove that T prime is finer than T and T is finer than T prime. Then they are equal then. Okay? Okay or not? So how to check? So to say that one is finer than the other, you just take some point and then take some basis element that contain the point and then see whether you can find a basis element from another basis that contain that point and contain in B. Okay? So in this case means what? You start with a point in the R2. Right? You start with a point in R2. Okay. You start with a point in R2. Okay. And then let's say we start from B first. So we take an open ball, covered it. Okay. So does there exist an open triangle that contain this point and lie inside this ball now? Can or not? Can, right? I can pick the side, the edge of the rectangle so that it doesn't exist the radius, for example. Okay. So in this case here, which one is finer than which one? So here we will see that T prime is finer than T, where T prime is the topology generated by B prime and T is generated by B. Okay. On the other hand, you start with a point in X, and then you look at open triangle that contains this point. Okay, you ask yourself, does there exist a basis element from B that contains this point and lies inside the open rectangle? Yes, right. Okay, you just make your radius smaller than the edge of your rectangle. Okay, then we will see that here we will say that T is finer than T prime. So they are really equal. Okay, so you can see that this topology here can be generated by two different bases. Okay, two different bases. And if you combine all the bases together, there's still a basis. There's still a basis because it's still satisfying the property of basis. Okay, does it make sense? Okay. Combine here means taking union. Okay, so there are two ways of combining things. You can take union or you can take intersection. Okay, there are two ways. All right. So far, any question about this? Okay, all good. So next, we will introduce some more topology on real number. So let's consider three different topology on real numbers. Because now we have a convenience way to talk about topology, which is just specifying the basis element. Okay, so we will just talk about what are the basis element in this topology. So first is the standard topology, which is the Euclidean topology. And what's the basis of this guy? What kind of basis you can take here? You can really just take open intervals. Okay, it is enough to cover everything inside your topological space. Okay, should we just write down what's the definition of open interval here? Okay, all the points that are strictly in between the endpoint. And second, we will introduce lower limit topology. Okay, so in this lower limit topology, we will take the point. We will take the left endpoint. Okay, the lower one. So we will include the lower point into our interval. So we took the half open interval where we close it at the lower end. So these are all the points from A to something less than B. Okay. And the third one we will take is called the K topology. So what's this K topology here? We start with open interval again, but we will add in some more stuff. So let K to be a set of 1 over n. And we will add in the complement of K. So meaning, and also, so we consider AB, all the AB take away K. Okay. It's like you are making a hole inside AB. Okay. If your AB is including the interval of 0 and 1, 0 to 1. Okay. So you are like making a hole inside it. Does it make sense or not? So for example, mm, for example, uh, -1 to 2 minus k. You know how does this look like? So you have a interval from -1 to 2. Okay. You take away all the 1 over n. So you are like making hole around. So let's start from 1. So you're making hole around 1, and then like this, converging to 0. Okay, 1. So there's a closed interval here. So you are making infinitely many holes inside an interval. Okay. And then try and show that, so exercise is try to prove that they are the basis, okay, for their topology. So they form a basis. So every point you can use one of the basis element to cover it. And then if you take two intersection, you can find another basis element that lie inside the intersection. Okay or not? Okay. So one job is to prove that, so exercise, prove that they are basis for their topology. Okay. Okay. Prove that they are basis for the topology. And lemma. So you can see that the topology of R, L, the lower topology, and RK, the K topology, are strictly finer than the standard one. Okay. So meaning they contain the standard one, but they're not equal. And RL and RK cannot be comparable. It's not comparable. So you cannot prove that whether one is finer than the other. So I give you sometimes maybe 3 minutes to think about this. Okay. So what do you need to prove here? So you need to show that RL contains R, right? Okay. But RL not equals to R. Okay, and then RK contains R, and RK not equals to R. And RK is not a subset of RL, and then RL is not a subset of RK. Okay, I'll let you think about it. Spend some time, you can talk with your friend. The type set knot is updated until lecture 8. I put up uploaded this morning. I just got it from Wenchuan. So if you are interested, do you need help or not with the typeset? Or you can work it out? You don't need. Okay, good. So I will update once Wenchuan sent me. Okay. If you found any discrepancy, just let me or let her know. Let him. Okay, let him or let me know. Okay, spend some time whether you can see this one. RK is what? So RL, just now we define RL is the lower limit topology, meaning we include the left endpoint of the open interval. Okay, half close. And then RK, what's the basis element here? We have open interval. We also have the interval that take away this 1/n sequence here. It's called K. Where's Sayed? Oh, holiday, this Wednesday. Okay. Any idea? 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 Yeah, any idea? So for the first one, to show that R, okay, R is a subset of R lower limit, how to show it? You need to show that every open set in R is in RL. Okay. But we know that this topology is generated by basis, right? So really, we just need to talk about basis element. Just talk about basis element. Because if you take the union of them, they are still living in the set, the basis set. So the element, the basis element in R is what? AB, right? Is this an element in RL or not? How? Huh? Including the A? What do you mean? So you want to prove that this element here is in RL. But RL is generated by what? half open interval. Okay. So can you build this set using the half open interval? How? Union of A plus epsilon. We can be more precise, right? We can just make a sequence, maybe A minus 1 over n. Does this work? Plus also can, right? Let me think. Plus is reaching. Oh, okay, yeah, plus. Okay, so plus B. Does this work? B is open. Yes, thank you. Does this work or not? So A 1 over n converge to 0, right? And then this one is approaching from where? So let me put the A, B here, right? Plus 1 over epsilon is where? A plus 1 over epsilon here. 1 over n. Okay. And then you can see that this A plus 1 over n is converging to A. Does it make sense? Okay. So you write the basis element in R as the union of basis element in RL. Okay, but union of basis element is still a basis element. Okay, no? Okay. Okay. How about this one? Show that RL is not equals to R. So meaning there's some open set or basis element in RL that cannot be covered by open interval. A typical thing in RL is what? XD. I'm sorry, XD, right? Like this. Okay. Can you find a point inside this set such that you cannot cover it by the open interval? X, right? So the claim is there doesn't exist an open interval such that X is in AB and AB is in XD. Does it make sense? You pick the endpoint here. You pick this closed endpoint. And you cannot find an open set, a basis element in V, which contain X. At the same time, this guy is contained. Does that make sense? Okay. 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 How about R in R? This one is easy because we also have open interval as the basis of RK. Okay, so we just pick the same open interval here. And because RK, one of the generator is open interval. Remember? So in RK, we have open interval plus open interval take away the sequence that over n, the sequence 1 over n. Okay. But RK is not equal to R. Why? So meaning there's some basis element in RK that cannot contain R, which contain a point inside the basis. Okay. What example you can take here? Let's consider maybe -1 to 1. Take away the sequence K. Yeah, I say that there's some point inside this set which cannot be contained by a open interval, and such that this open interval lying inside the set. What point is that? 0. So there's no open interval. This one is in R, such that 0 is in AB and AB is in minus 1, 1 take away k. Why? Why is this true? Why is this true? So let's draw this out. So you have minus 1, 1, right? Okay, you take away all the sequence that converge to 0. I mean, all the 1 over n that converge to 0. But 0 here, I don't take away, right? This is a point in minus 1, 1. So here, 0 is inside here. Okay, I just take away 1 over n for n large. And I said that there's no AB. Okay, there's no AB that contains 0. And then this open interval lie inside complement of k. Is this true? Why is this true? Why is this true? Yes, Archimedean property, because you can consider this epsilon here, b minus a. Right. For every epsilon, there exists an n such that 1 over n is less than the epsilon. So no matter how small you make this b, right, I can always have some 1 over n inside this AB. It contains something that's not in the original. Okay? Does it make sense?
It's not the 0 not inside AB, it's the AB not inside the subset of minus 1, 1 minus k, right?
Yes. You can have AB containing 0, but the AB is not contained in the. Yes, because you always contain some 1 over n, which is not in this. So, does it make sense? Okay. Yeah. So you can use similar definition example to prove these two. Actually, you can use similar example to prove these two property. Okay, I'll try write it out in the notes, but you should think about it because it's really some example that already given above. Okay. Okay. Before we go to the next part, we finish up with this sub-basis here. So let's introduce the definition of sub-basis before we leave basis subtopic. So what's a sub-basis here? Sub-basis, sub is like smaller than the normal basis, right? Okay, so let's see how is it smaller. So sub-basis X for the topology on X is a collection of subset of X whose union equal X. Okay, and how do we define this topology here? Okay, so we have a basis, right? Then we need to say how is the base, how's the topology generated by this basis? Basis. So the topology generated by this basis is defined to be the collection T of all unions of finite intersection of elements of X. So meaning what? Meaning you have a sub-basis, okay? All the elements there, you can take their finite intersection Yeah, finite intersection of open set should be open. And you can take union of them. Okay. What we have before is what? What do we have before? Topology generated by a basis. It's just union of basis element. But here we allow intersection first. Okay, we intersect and then we take the union. Does it make sense? Yeah. So how should I write this? Yeah. So maybe I can write it like this. So T equal. I think it's not a good way to write it. Huh? First is like you have finite intersection first, and then you can take arbitrary union of them. Can you imagine what am I talking about? Yeah. This T is closer than the T generated by the basis. Is it closer? We have intersection. Should be final, but I never saw it before. So waiting. Try and prove whether it's final or closer. Yeah. Mm. Yes.
Let's say they are disjoint. Then if I take the intersection with the empty set,
Correct.
then so I take the union of empty set or I take the union of these three sets.
What do you mean? I think union.
The union of intersection of
Oh. Oh yeah, sure. Yeah. Uh-huh. Yes. Uh-huh.
Union of finite intersection is the union of A, B, and the empty set, or just the empty set?
You say suppose S1 intersect S2 is empty, right? Okay, and then
Union S1
depend. You can so in T here, what can you see here? You can take X1 intersect X2 and then union X1. Also can, right? You can take X1 intersect X2, X intersect X3, union X1 intersect S2, right? And all possibilities. As long as your intersection is finite, union is arbitrary. Yeah. So if you are union with some empty set, then it doesn't, yeah, it doesn't contribute to the union. Hmm? So this is final, right?
Intersection with, because you all finite intersection, and then just take everything is still inside there, and then you have some other things which is come
Smaller.
Smaller things.
Okay.
Right.
Kind of makes sense. So if you have I mean, okay, final actually it just comes from the fact that it contains the original x1 to x. Yeah, it just contains the normal basis. Yeah, but now you consider all the finite intersection and union of them, not just finite intersection, but also union of them. Yeah.
And it still contains.
Yeah, it still contains the original basis. Yes, yes, still contains the original basis. Yeah, yeah, makes sense. So try and try and put a lemma here. Position. The G generated by sub basis as a basis is causal then the topology generated by, okay, let's put X here. The topology generated by X as a basis is coarser than the topology generated by S as a subbasis. Okay? The subbasis one contain the basis one. It's a finer than. Okay? Can follow? Yeah, try and prove this. Okay, so far any question up to here about the basis and coarser, finer definition? Okay, if not, we introduce another definition here before we jump into closed set definition. So we will define something called the, so let me move downward. So we'll define what's a subspace topology. Okay, let's motivate this subspace topology a bit. So for example, real line, okay, we can consider Euclidean topology here, okay, or really just now we talked about basis description about Euclidean topology, right? We can just take open interval, okay, or the collection of open interval generated, topology generated by open interval. And really, let's say we know the topology on R already, okay, with the standard one, or standard topology. We can really restrict our set. So we can consider some subspace here. For example, 0 to 1. How do you talk about open set in 0 to 1 here? Okay. Or if I consider close, okay, on the left endpoint here, how is it an open set looks like? How does open set looks like inside here? Okay. So we will define, that X be a topological space. And if Y is a subset of X, okay, then I claim that the collection of intersection between Y and U, where U is an open set in the topology, is a topology on Y, okay, which we call the subspace topology. So to check topology, remember what things you need to check? How many property you need to check topology? 3 things, right? So empty set need to be in there. Right. Why is the empty set is there? Because you can pick U to be empty. The whole set have to be in there. Meaning Y have to be in there, right? Okay, so why Y is in there? Choose U to be X. Correct? Okay. Because X intercept Y, you should get Y because Y is a subset of X. What else? You need to check finite intersection is still in there, right? So if you take finite intersection of them, what do you mean? Y intersect with U1, Y intersect with U2, Y intersect with U3, and then you take the intersection of these two, all these. But what are these? These are just Y intersect with finite intersection of UI. But finite intersection of UI is still open because it is still in the topology. Right? So still looks like y-intercept some open set in T. So similar for the arbitrary union. Okay. Similar for arbitrary union here. So so in other words, with this topology here, Y is called subspace. So this is a bit different from the vector subspace. This is just a normal topological subspace of X. X open set. What is this open set here? So your open set consists of all intersection of open set X with Y. Okay. So let's jump back to this example here. What are the open set in 0, 1? So let's write down what is the open set in 0, 1 here. So what are the open sets here? Can you tell me one? One by one. Dingy, give me one example of open set here. 0 to 1, you want close or open? Open on both sides. Okay. Why? Because you can write it as the closed interval 0 to 1 intersect with the open interval 0 to 1. But 0 to 1 is an open set in the standard topology. Okay. Try another one. 3. Hmm? Zero to 1/2, open or close? Open on both sides. Okay, so why is this open set in the closed half open 0 to 1? Because you can write it as 0 to 1 intersect the open interval 0 to half. Okay. Let me change another question. Why the open set, the half open interval from 0 to 1 is open? Simple. Why is this open? Why is this open? I just introduced the definition, right? So you should be able to write down as the subspace intersect with some open set, the larger space, ambient space. How? Okay, I call you Jingbo next time. So you can take this intersect with the open interval from -1 to 1. Yeah. Good. Huh? Sorry? Yeah, you can. Yeah. Or you can, like what Ziqian said, you take the whole real line also can. Yeah. But yeah. Okay. -1 to 1 is open in the larger space. Okay. Can you find something that's not open here? I think there are quite a few things you can find, but need some construction. Never mind. Okay, let's see. Okay, so before we close down on this topic, I want to talk about, let me see, two property. Okay, maybe we won't prove it because quite obvious or quite tedious. So first property is, once we get this topology, right? Remember what's the discussion about topology we did? We have topology, and then we ask about basis. Okay, so you can ask about basis. What are the bases? Who generate this subspace topology? Okay, you want to guess or not? You want to guess who generate the subspace topology? Say we know how to generate the basis, the topology for the original space. Okay, then really, you can just consider the intersection. Okay, intersection of Y with this basis element in the original space. Okay, and then this will form a basis. Okay, so you try and prove it. Okay, I think it's quite intuitive, right? You just take the basis element from the original set, okay, and then intersect with Y. And then this guy should generate the basis downstairs. But to show that this is true, you need to prove it. Okay, you need to prove it from the definition. And another similarly obvious lemma is let Y be a subspace of X if U is open in Y and Y is open in X. So there's like a transitivity property here. Then U is open in X. This result seems a bit direct, but it's quite important that it is not always true that U is open in the subspace topology, meaning U is open in the larger topology. Right. This is already given by the definition I showed you just now. Okay. Although we know that the half open interval here is open in the subspace topology, but is it open in the standard topology on R? Is it open? It is not. Okay. Is it open or not? All right. Because to be open, what do you need to do? A is in A. Right. There's a matrix topology, but later we will. We also introduce open, right? Did we introduce open definition previously? Or we just say that open that satisfy all those properties. So yeah. Okay, so any question before we take a break? Any question before we take a break? Okay, so I make a remark here. So remark here is U is open in Y doesn't always imply it's open in X. Okay. So only when Y is open in X, then you can have this transitivity property. Okay. No question. Let's take a break until 2:09. Yes。第一个 lemma 的 proof， 这个，OK， I see 啊，对，对，Yeah，where B alpha is in T， 对，对，没错，对，对。哦，你是那个意思哦，Yeah，right，是basis for T，correct，对对，它是basis for 这个 T，这样，嗯，Yeah，特别的是这些是 basis element 哦，其实不是特别在它在提的说它是 basis element 啊，因为你要有 basis element 你才可以开始用这句话，对不对？Yeah，对，你对，对。对嗯还没有做完哦，别的呢？啊然后所以呢，所以哦，Ryan 啊，他讲他出了我哦，
这个想办完蛋，这个不可以再打，竞争，对，都是在
他知道那个尔康是谁没？对啊，
这个话，然后讲，因为最后讲你是 interpretation of 什么 set，
谁有 set？
就是这个 open question 给我们这个去对就。
哦，
他跳了，他自己想到什么就讲，他其实都不成型。
他真的是很像教授了。教授就是想讲什么就讲什么。怎么？呀，
因为我想讲，
想讲什么？
这也是这样子。因为我想讲，我什么好像不是这样，
三
没有关系。
我上面有这题没？
那一题，
哪一题？
equivalent 嘛，
对，
等于那
只是 bound 罢了，不是？这是 algebraic bound，不是？你画的，你把它画出来。
我没有啊。RN 那里可能画的。
对了，Rn 嘛
第三题是哪里？
第二哎，
那三
对呀，那个是 Rn 哎，对，
哦，那三个啊，另外，
耶，
也就是中间有三个东西，我忘了。
嗯，
它是哪这三个？是
讲第三题啊，
哦，
第二题，那个是第三哎，
这
第二是 comparable matrix，
comparable，
耶，那个肯定 matrix space 的对，那个 open 是 in matrix space， 对，没有错，对，两种 open。都可以吧？我只是上面放 E， 上面放 B 减 A 有关系吗？
第三没有少，不是少过一的话，它就出 B 了。
我想一下，哦，诶，我想一下，哦，你是那个意思？OK，我觉得 make sense，我觉得可以，对， 要考虑一下那个。
对呀，
但是如果不考虑那个的话，我只是加一些 MD set 进去吧。
也是
对呀
可以，
对呀，
也是可以。
什么什么？
哦，不是，就是这个，
哦，
等一下我看一下这个
看到好像有一些问题。
this one，
对呀。
他说要把这个 E 写成 B 减 A，因为怕等一下这个 B 是小于 E
哦，true。
啊。
哦，是，B 减 A，yes，B 减 A，B 减 A 是。
But my point 是，就算这样也不用紧，因为你只是加一些 MD set 进去吧，
嗯，
加一大堆 MD set 进去
是咯，没有差，没有差。对。
都可以。
哦，
说你可以写成啊，
不要紧，
什么
说它分子是不管什么号码都可以的，
哪一个？
就是刚刚你讲 B 减 A 也是一个嘛，
对，
收上面随便一个号码都可以。
应该是对。
对，因为你这个
as long as 你要 produce 一个
嗯
那个decreasing sequence 进到
，as if 你这个东西大过这个东西的话，你就自然而然就不会有这样的 interval 了。那 interval 不存在。
你没有这个的 point 是来你要 produce 一个
对，往那边
啊
慢慢
sequence 的
extend 它过去
converge 去
那个 A 那边。
哎，这不是应该-
没有 plus
是从那边，
minus 是这边，
minus 是
这个 plus 是从这边，从右边往
不然你会 include 多东西进去。
啊，对啊。
等一下，因为 A 随着 N 大不是。哦
A 减
OK，OK
A 减 E 在这边，所以你不会把 A 减 E 加进来，但是这边没有 A 减 E。
哦，OK，
可是
虽然你还是往那边方向，但是你会把它们加进。这个的原因是，当我在加的时候，前面一个是包在后面的里面，所以
他的
你的吗？
厉害，其实我不知道怎么讲呢，我还是有点除了就是讲
哪个地方？
我这两个这两个 interval 以外的东西都是 MD 的。
什么？你在讲吗？
我不懂为什么你是讲，我不懂为什么你讲它这个 B 过后的东西都是 MD 的。
不是，就是不抵。如果我加了过后，不是这个东西会大过 B 吗？then 这个 interval 不 define，因为没有一个号码可以大过小过大的那个又小又大又小
大
过大的
的，小过小的。
啊，小过大的又大过小的啊，contradiction。对啊，没有这个东西。
没有关系。
MD 噻。
还有时间。
找一下那个什么。写到，给我抄一下，不好意思。
不是。这个东西，我觉得你是要讲2NA 跟2N 减 1A。现在是MAT2 没有 rational 嘛？你这里这么，你 output 还有 rational。
想加
只要直接弄一个 add-on irrational 的 budgeting 嘛。
是啊，B7哦。
那你起步的时候，
对，我慢点再想一下。我忽然间 recall 不出来。
其实第三题的那个 C 题，我是我有点 confused， 那个其实那题目在问什么？你是讲把一条线的那个
我们可以讨论
看成那个equivalence relation 是吗？我自己是 define， 因为一个圆嘛，应该经过那个 origin 嘛 ，right？ 然后这个情况呢，
我们可以 discuss 那个。可以，我们 discuss 那个。
我就在想，我有没有弄错了？
所以全部人有在 ？Are you guys have you guys tried assignment 2, 3, 3 啊 3 part 3啊 3 part 3 3C okay. Have you guys tried this? What's the question asking?
Define a pseudo-metric
Define.
Unit string.
对
pseudo-metric classes are the set of
on On lines, right? On line.
On the S 然后 equivalence plus 要那个 set of line。
Okay. Rephrase. Lost in translation. Wait, let me check. I can tell you what you need to do. I can even tell you what to define. I'm not sure there are other solutions or not, but I can try and give you one solution. Okay, so define a pseudometry on Sn. Okay, not just S2. S2 or Sn? Sn. And that makes Seng in Rn+1 through origin into a metric space. Okay, so first you need to understand what this question asking first. Okay, so this question asks you to build a pseudometric on Sn. Okay, what does pseudometric means? There's a definition on the first line. It is a metric, except it doesn't have the first metric definition, which is rho xy equals 0 doesn't need to imply x equal to y. So you can have two different points, but you have 0 distance between two of you. Okay, so this is pseudometric. But this is not any random pseudometric. You need to mix the set of line in Rn+1 through the origin into a metric space. Okay. So you need to define such that you make the lines in Rn+1 through the origin into a metric space. What does this mean? So meaning I give you any two lines, not random line. Line have to pass through the origin one, and then give me a distance. And then this is a metric space. Okay, so this is what you need to do. So meaning you need to connect pseudometry of Sn to a matrix or set of line first. How to connect these two? The connection is the one that I give you in the hint. Okay, why the hint will give you this connection? So what's this hint here? The hint here says what? Any line on Rn+1 is completely determined by the intersection with Sn. Okay, you think about this. You have line through origin. Okay, this line should intersect with the unit sphere. Should or not? Should, right? This line is infinity line, not finite line. So you should pass this circle, this unit sphere circle. But what? But what is this 2 point here? You can really describe this 2 point as x and minus x. Okay, x here is Rn. Don't think about just one variable, it's Rn. Depend on what n. But for example, in this case here, this one is R what? R2, right? This is R2, right? So here is R2. So this sphere here is S1. Correct, no? Sn and R+1. So this sphere is x1. In particular, this point here is what? 0, 1. Then the other point is 0, minus 1. X and minus x. Okay, and then you can prove that this is true for general n. Okay, x and minus x. What do you mean?
Want to define a pseudometric space into metric space, and then you need to define the space such as you under some equivalence relation, right? So under that space, the equivalent relation implies that the 2 points are same, and then you can map it into a metric space.
Yeah, seems like it. Part B. What does part B say? Yeah. Okay, what does part B ask you to do? Part A and part B, what does this question ask you to do? So A, it just says that if you have a row such that row xy equal to 0, okay, and we will collect x and y together as an equivalent class, and then show that this is an equivalence relation. Okay? So meaning I collect all the points, all the different points together when their distance are 0. Does it make sense? Okay. And then second part, if x star is the set of equivalent classes under this relation, meaning what? So I have set right x here, okay, and then I collect partition, okay, those who have distance 0 with each other, meaning maybe let's say what? Okay, just say like that, and then x star is the partition set of partition. Okay, so we see all those distance with 0, with distance 0, all those points with distance 0 as one element, right? Set of equivalent classes. And then we show that row xy depends only on the equivalent classes xy. What does this mean? Meaning if you take different representative out of okay, so let me write this for you. So you write it down. O xy depends only on the equivalent classes of xy. What does it mean? So potentially you have equivalent classes for x and y, say x x1 x2 so on, and then y y1 y2 and so on, right? Okay, so you need to show that row of xy is equals to row of any xi yi, okay, for example. Does it make sense? For all row xi in equivalent class of x bar, and for all yj in the equivalent class of y bar. Okay. They could come from two different equivalent classes. Okay, not necessarily coming from the same one. If coming from the same one, then it's easier. But right. Okay. And then second part, somehow you need to use this two knowledge, right, to define this pseudo matrix here. Anyone has any idea? I've tried. Can give some hint. Let's see what hint. Yeah. So what hint we can give here? So what hint we can give here? So I can define, so this row here, right, should take points in Sn and then split out some real number. Okay. And I want to make it pseudo metric. So you can try and define this. So you have this 2 point here, which is equals to the minimum of length of x minus y, comma length of x plus y. Okay, you can try this. And you can check that this is a pseudo metric on Sn, Sn, yes. So when is it equal to 0 in this case here? One of them is 0, right? One of them is 0 means what? One of them is 0, it means what? Is this one equals 0 or this one equals 0, right? But this absolute here meaning we take the normal Euclidean length. So that is a matrix. So meaning either y equals to x or y equals to minus x. So it induces a pseudo metric on this space here. Yes. Does it make sense? No, I mean 不是简单，就是你如果拿到诀窍，你肯定是简单的。就是这一个 part 你想不想得出来吧？对，你有什么方式？
可是我觉得应该是一样的。我是，
那你跟我讲，你肯定要 define 这个东西出来的，所以你要跟我讲你的 role 是什么。哎，那你就
我一
check
开始我是写一串文字先，
文字，
然后我原本后面有加，然后我又除掉，可是我觉得应该是对的，就是
不是你 try 看。
origin 嘛，你这样子一个
Yeah.
嘛，然后一个 line through，
呀，
然后它either 你是 same point 0，或者它是两端的 point，它一定是 two 了，因为 unit sphere 嘛。这样子或者这样子，
好像这样子呢。
这个是一个
哦，OK 啊，
你一直是同样的 point 的话，肯定 distance 0，要不然的话就是它这样子，然后这边两对面的话经过 origin， 这样子它只有这个情况，它的 distance 才是 two 嘛。
distance 2是什么呀？
是不是？啊！
你就故意让他，你就来
0或者2，0跟2这两个情况都一定是它是equivalent 的。
OK，then in 那个 case 你要 check， 喂啦，这个 case 我没有 check 过它是 metric 吗？还要另外 check 它是 metric。对 ，OK，you check 就 OK，you check 就可以。check pseudo metric， 但是你另外两个 property 是 metric 的 property 嘛，对不对？对啊，你要 check 啊。喂，等一下，先让我 check 一下啊。哦 ，OK，yeah。So 如果 if you check this one is a pseudo metric already, then by part B it will induce a metric on the equivalent class. So the equivalent class on Sn, when you identify the antipolar line, is really just the line through the origin. Does it make sense? Make sense or not? Does it make sense? So you see, if I identify y equals to plus minus x, what happens here? I'm identify the antipolar line. This is what we call the antipolar point. Okay, because they are opposite to each other. And then if I identify this 2 point here, it represents the single line. Okay, no? Because once you draw a line, this 2 point is fixed already. Okay, so you identify this 2 point as 1 point. So meaning you identify the line. Okay, identify the 2 points as 1 line. Yeah, so the claim is you need to check this is a pseudo matrix. And then by part B, it will induce a metric on the equivalent class here. So the equivalent class here is exactly the set of line through the origin. This is the logic. Does it make sense? Yeah, so they have, so Gary and Chuan has got different role if you want to ask them what role they use. Basically, they really just, so they just declare if you are the antipolar point, your distance is 0. And then if you are not, then 1. So meaning at 2, you use 2, you use 1. So meaning distance between every 2 different lines is just 2 or 1 constant. Yeah, I also can do that. This one is moving. This one a bit moving. Depend on your x and y. This one. Yeah. So they make it like a direct delta like that. If equal, then 0. Not equal, then 1. Not equal 1. Not equal 1.
Else, if you are here, else you are here.
Like that direct delta.
Meaning there are 2 points lying on the same line that they are in the same.
Yes, they are. Yes.
The line that pass through origin.
Yeah, pass through origin.
Yes. Yeah. You can try. Yeah. So that's why I say there's no only one solution. You've got a few solutions. As long as you satisfy those property. That's fine. Okay. And okay. Okay. You can do as creative as you can. Okay. As long as it works. Okay. So let's continue. Maybe I'll go a bit over time. If you want to leave, feel free. All right. So where is it? Okay. We will introduce a closed set now. Okay, let's introduce closed set. So how we introduce open? When we introduce open, we just say that open set will satisfy some property. Okay, like empty set is open, whole space is open, okay, open union of open thing should be open, finite intersection of open thing should be open. And with this open set, we can pull out some basis, right? We can pull out basis element, okay, to generate the topology. And now we will return to talk about closed set. And you can observe that these closed set definition or limit points, right, resemble a lot with metric space, the closed set in metric space, and the limit point in metric space. Literally the same terminology, but in this chapter here, we will use open set, closed set to talk about limit points. Okay, so let's define closed first. So what is closed? Actually, the definition we gave in metric space is quite sufficient already. So a subspace A in a topological space is closed if the complement is open. Okay, it's the same. But note that the open here is different a bit already. The open in the metric space is open in the sense of metric, but the open in here is open in the sense of topology. It's just some collection of subspace that satisfies some property. Okay, so this is the difference here. Let's discuss some example of closed set. Okay, for example, what are closed? Closed interval are closed. That's why we say closed. Why? Why? What's the complement of this closed interval here? Youngin? You take a real line, right? Okay, you take an interval AB. This is the closed interval here. And then you take the complement. So what's this complement here? Yeah, what is it? Yeah, minus infinity to A, open at A, union with open at B to infinity. Right. These two sets are open. Union of two open set is open. Yeah, no? Okay, so the complement is open. What else? For example, this set here, y equals to x squared, is also closed. Okay. Why is it closed? You need to show that the complement is open. But what's this complement here? What's the complement of this guy? Yes, it is something that's not equal. So meaning you can take the union of point which is y greater than x squared or y less than x squared. And then show that this is open. Okay, write it as a union of basis element, or you can show from the open definition. Yeah, what does it mean by open in the basis element? So what's the basis for this topology? Just now we have give two bases, right? Either you can take open circle, open ball, or you can take open rectangle. Okay, and then show that it's open in this sense. Actually, this kind of closed set is very important in algebraic geometry. Okay, let's do some advertisement on algebraic geometry. So this set here will form what we call Zariski closed set. Okay, so it forms a topology actually. Okay, later we will discuss how closed set will form a topology. Okay, so we use closed set to define topology because in algebraic geometry we are interested in the solution to algebraic equation, right? Solution to algebraic equation. But to solve a solution of algebraic equation, you need to solve the equality, right? Something equal to something. So it is closed. And what else? What example we can give here? So for example, we have gave three. Let's do the example. For example, what are the closed set in finite complement topology of X? Can anyone recall what the finite complement topology is? When we declare a set to be open in that topology. Finite complement. So meaning complement. Complement of that set is finite or it is equal to the whole set. Right? So what is the closed set here? Closed set means what? The complement of this set lies inside the topology. Right. Let me write it down then. So what's this topology here? It's all the subset X such that X minus U is finite and all X minus U equals to X. Okay, so what things are closed here? So when you ask what set are closed in this topology means what? The complement is in the set. So a closed set contains what? You try to think about it. So if let's say C is closed in X, meaning what? Then X minus C is open. Okay, meaning it is in the topology. I don't know. But if X minus C is open, means what? Then X minus C, the cardinality should be finite, or X minus C is X. Implies what? Implies the cardinality of C should be finite, or C is equal to X. So these are the closed set in this finite complement topology. Does it make sense? Make sense or not? You should be able to follow this simple logic. I haven't put any concept here yet. I just use logic. If something you don't know, you should ask, because you might be missing some important definition. Any question? Question? Yeah.
S minus C.
Why is that true? Huh? So y x take away c is x. So this is set theory. So why is it true? Huh? Hey, what do I do? Huh? Oh, equal to c. Sorry. Yeah. Okay, why is this true? You have a set x, right? You can use Venn diagram first, but to be precise, you need to use the membership, right? So let's say c is inside x, right? So x take away c is what? You take the outside one, right? And then x take away this guy, so you come back to the c. Does it make sense? But you need to use the subset inclusion to show it to be precise. Huh? This is just a Venn diagram.
So
What am I doing? Wait, which one? This one, huh? Oh, this one is the condition from the finite topology, finite complement. So your u have to satisfy this finite condition or x minus u equal to x. So the u here is x minus c. So I need to make sure that x minus c is x. But on the left hand side is c, on the right hand side is x. So meaning your closed set must be a finite set, or your closed set is the whole space. This is what I meant. Make sense or not? Does it make sense? So this x is not because of the calculation here. This x is coming from the topology definition. Okay. Either your complement is finite or the complement is exactly the whole space. Remember why we include this definition again? Yes, we need to consider the empty set. Otherwise, the empty set won't lie inside this topology. If your x is, let's say, uncountable, right? No. Okay. Okay. Yeah. You're right. So this one is coming from the definition of topology. Okay. But this one is to calculate the left-hand side. All right. Okay, good. How about one last example before we go into property? How about discrete topology on X? What are the closed set here? What are the closed set here? What happened in discrete topology? Every subset is open. So what are the closed set? Huh? Empty? No. Everything. So since every set is open, every set is closed as well. Why? Because the complement of your closed set is some subset in your topological space. But you declare that set to be open as you declare everything, every subset to be open. That complement has to open as well. Okay. Does it make sense? Got question? Every set is closed because complement is a subset of the original set, but you declare every subset to be open. In particular, that complement also have to be open. Okay. Right. So next, recall the familiar theorem we have, but we will replace every open with close. So let X to be a topological space. What hole? Okay, what hole? The following holes. So first, empty and the whole space are closed. Okay. Why? X minus A is open. X minus X is also open. Okay. And then arbitrary intersection. of closed set are closed. Still remember the De Morgan's law we use for metric space? Because arbitrary union of open set is open. Okay, so you want to check for arbitrary intersection of closed set, right? What do? You take the complement of it. Okay. So complement of okay, let me write down. You guys look very blur. I'm very scary. I'm very worried, not scary. I'm very worried. So let's take this closed set. What is this? The complement of this is the union of what? X minus Ci. This is what? De Morgan's law. Okay. But you know that each Ci are closed, so the thing inside should be open. Right? Union of open set is arbitrary open is open. Okay. So this guy is open. So you check that the complement is open. Okay, part 3. Similarly, you can see that finite union of closed set are closed. Okay. Also will involve a De Morgan's law. Okay, so you take X, take away finite union of Ci. Okay. What is this? This is finite intersection of X take away Ci. Okay. Which is open as well. Okay, so yeah, so closed set. So you can, in a topological space, right? You can really specify all the open set, or you specify all the closed set. So there are two ways to define topological space. So the one I told you just now, the Zariski closed set, which is the zeros of sub-polynomial algebraic equation. They form a topological space, which we call a Zariski closed topology. Okay. Because in algebraic geometry, we want to solve equation. So we will consider closed set more naturally, okay, than open set. See. Okay, so let's continue. We have a similar definition. Okay, so now we will explore some property of closed set. So first, we will say that if Y is a subspace of X, we say that a set is closed in Y. Okay, is closed in Y. So last time we said if it is open in Y, it is open in the subspace topology, right? So in this case here, we define what is closed in Y. So we say that if this is a subset of X, we say that a set is closed in Y. If A is subset of Y, okay, and A is closed in the subspace topology of Y. Okay, meaning what? That is, if you take Y minus A, is open in Y. So meaning, if you want to talk about a set that is closed at subspace, okay, then really you need to use the subspace topology just now. So you need to imagine the subspace topology we have just now is the subspace intersect with the open set in the whole space. Okay. So what time is it? 2:45. Okay, so there are two lemma here. So let's write down the lemma and then we discuss a little bit on them. See if we want to prove it or not. So first theorem is if let y be a subspace of X. Okay. So meaning what's the subspace means? It's not a vector subspace. This subspace just means that I have a subspace topology from X. How we declare why the set in Y open? If I can write it as an intersection of Y and the open set in X. Okay, remember the example we have on half open 0, 1 just now. So if we inherit this subspace topology from X, then a set A is closed in Y if and only if A equals to C intersect Y, where C is closed in X. Closed in X. So I think it's a subset. Closed in X. Okay. Is this similar to what we have on open set or not? We say that something in the subspace is open if you are the intersection of the subspace with an open set. Okay, we have similar description of offset as well. Another similar thing is theorem. Let Y be a subspace of X if A is closed in Y and Y is closed in X, then we have this transitivity property. Then A is closed in X. So this is similar to what we have just now. If A is open in Y, Y is open in X, then A is open in X. Okay. Okay or not? These two theorems are quite easy to prove. Okay, just use definition. Just spell out the definition. Okay. Any question or not? I'm trying to skip the proof. But I will write down in the lecture notes, and you should also write it down. Try to practice and write it down. It's just some definition checking and then easy construction. But do you get this two line or not? You need to get the moral first. Get the moral and then prove it. Do you all get this? What this two trying to say? Yes or no? Okay. So I want to say if you replace all the closed word with open, it's also a theorem. So meaning what? Closed set and open set bear the same property. Okay, so that's why we can really just if you want to talk about topological space, you can really just talk about open set, or you just talk about closed set. Okay, if there's no question about this, let's continue. So proof will be left as an easy exercise. So you just spell out the definition, or the complement is open, what complement is open, and then check whether the other complement is open or not. Okay, next, we will recall some very reminiscing definition. So, given a subspace, given a subset of a topological space, again, okay, we can define the interior of A. Remember how we defined interior of A last time? How we define interior of A last time? For metric space. How we define interior for A? For every point in the set, you can find a open ball, right, inside A. So in this case here, what's the open ball? Okay, so we just define it as the union of all open set contain open sets contain in A. Okay. So you really need to think about this open interval 0 to 1. Okay. You can, how you build the open interval 0 to 1? You can take all the union, all the open interval in 0 to 1. Okay. This is what it tries to model. Okay. You can take union of all open set that contain in A. How about the closure? Okay, last time how we define the closure? The set A and its limit point. Okay, but we haven't defined limit point here. But what we have here is closed set. Okay, so we're gonna define this to be the intersection. Okay, intersection of all closed set containing A. Okay, so I mean, let's write down this in word, right? So A bar should be equal to the intersection, okay, of all C alpha such that or for all C alpha that contain A. So like this. Okay, intersection of all. How about the interior? In A should be defined as a union, okay, of all open set. How do we write open set here? Let's put O then, O alpha such that OA is in A. So can you see this? What's the difference between these two definitions? One of them we use intersection. One of them we use union. Okay. And then you can see that how this set includes or contains A. Okay, includes or contains in A. Okay, you can think of it, this C alpha, right, is potentially bigger than alpha. So if you take intersection of all these things, right, it's kind of like getting smaller, smaller, and smaller. How about this one? If you take all the open set that contains in A, you are somehow like growing. Okay, somehow growing. Okay. Right. So some remark here. Okay, what time? Okay. So some remark here. So clearly, okay, clearly, interior of A is a subset of A, and A is a subset of A bar. Is this clear now? What is in A? Union of everything that's a subset of A. So if all A is in A, union of them should be in A as well. Right. Okay. How about A bar here? Closed set that contains A. In particular, all the closed set should contain A. So A live in every closed set. Does that make sense? So since all A live in A, union, sorry, this should be alpha. Since all alpha live in A, union of all alpha should live in A as well. Okay. And since A live in all the C alpha, so for all alpha here, also for all alpha, it's true for all alpha here. So this is true for all alpha. And on the other hand, we also have A is in C alpha for all alpha. Then A should be in all the intersection of all alpha. We also have intersection means. means you are in every set. Okay. Okay. And this is the first remark. How about second remark here? So if A is open, A equals to in A. Why? Because A is one of the open set. Because A is one of the open set. So you will include A as your into your union. Okay. So since one of the element in the union is A. Since one of the element in the union is A. So you have union the largest guy. Take union of the largest guy. And if A is closed, what happened? A equals to A bar. Why? Because you intersect with A again. A is one of the closed set. Okay, so you get A. So you see, this two definition, right? Previously is a result from metric space, but here is a result from the definition. Okay. Last time we take it as a definition, but this time is just a consequence of the definition. Okay, it's a consequence of definition. So if I want to write here, it seems one of the elements in the intersection. Okay, is A. Right, you intersect a lot of things that contains A, and then you intersect A. So A must be in all of these guys. I mean, okay. Okay. Any questions so far about this property here? Any questions so far? Oh, okay. So another motivation I gave before we drill into the theorem. So if A is a subset of Y, the closure, okay, the closure of A in Y and the closure of A in X will in general be different. Can you quickly give one example or not? It's the same example we can take from just now. The running example is the 0, 1 in R. So 0, 1, the closure of 0, 1 in, so okay, let's don't write that notation. Maybe it's a bit confusing. So just write it in word. So what's the closure? What's the closure of no class is it? Oh, okay, never mind. So what's the closure of this half open interval in let's say R? Should be a closed interval 0 to 1. Okay. How about the closure of this half open interval in the subspace? It should be itself. Okay, so they are different here. Okay, try and show it. Try and show it. Yeah. Okay, so let me put this theorem here. Let Y be a subspace X. Okay, and then let A be just a subset of Y. And so normally when we put A bar, right? This bar here, usually we say this is a closure in the bigger space. Okay, it's in X. X. Then the closure. So we don't have any notation for closure of A in Y. This should be equal to A bar intersect Y. Okay, if we assume this definition, right? I mean, assume this theorem, and this is the result we get. As you can see the example here. If we assume this theorem, and this is the result we get, because this is really the A bar, okay, 0, 1 intersect with your subspace. Okay, so we need to prove this. Okay, once you prove this, then you will know why is this true. Otherwise, you can check from definition, also works. But if you prove this theorem, then it will works. So I also want to skip this theorem proof because it's kind of checking definition stuff. Okay. 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 So let's left as an exercise. So more importantly, you see, I left an exercise. Why I left an exercise? You need to know why I left it as an exercise. I'm not torturing you, because I don't want to torturing you. Because you know why? Because it's just some repetitive argument here. Just using definition of closure and then just change some set. Okay. So what's the key here? The key point here is do you know how to apply this theorem or not? Okay. Let's say I have a subspace, I have a subset of Y. I want to find the closure of A in Y. How do you find it? Use this method. You need to find the closure of A inside X first, and then intersect with Y. So, for example, the example I gave just now. Okay, I have that half open interval as a subset of R. I want to find the closure of that half open interval in itself. So first, you need to go and find the closure in the larger spaces, which is 0, 1. And then you go and intersect with the subspace. So you reduce to the half open interval again. Does it make sense? Okay. Any question or not on using this theorem or trying to prove it? Is it clear on how to prove it? Is it clear? How to start? I mean, even how to start. Is it clear? So you need to take some closure. Let B equals to closure of A in Y, and then show that B is equals to A bar intersect Y. Okay. So if you want to show that two sets are equal, then you need to show subset inclusion. Does it make sense? Okay. Yeah, the proof is not very enlightening. It's just playing around with set theory and definition. Okay. If okay, let's continue some more. Let's see if we can get to Hausdorff space before 3:30. Yeah. Okay. That's right. So next definition is also very reminiscing. So let's say that a set A intersect a set B if the intersection is not empty. Okay, it's not empty. If we say A intersect B, that means the intersection is not empty because we try to reduce some word inside our statement of theorem. So let's A be a subset of a topological space. Okay. First thing is X is in A bar if and only if every open set U containing X intersect A. Does this recall you about property in metric space? Right. If you are on the boundary or you are in the set, then every open ball around you should intersect with some point in A. Okay? Either that point is yourself or you are a limit point of somebody else. Limit point of A, I mean. Okay. And because we have a more descriptive definition, not descriptive, explanation on topology, so we can make this more precise. So suppose the topology of X is given by a basis. Okay, let's say our topology is generated by basis. Then we can reduce the statement to just checking the basis element. Okay, no need to check all the open set. We just check on every basis element is enough. We just check on every basis element is enough. We can try and prove this because it's quite interesting. This proof. Okay, remember that last time how we proved this? We use open ball, right? We use open ball to prove it. But here, no open ball, just open set. Okay, so how are we gonna prove this? So let's prove the first one first. So instead of we want to check for all open set, right? Okay, we can turn this sentence into X is not in the closure if and only if there exists some open set containing U, containing X that does not intersect A. Okay. Is this obvious or not? Is this obvious? What is A bar? A bar is closed or open? Closed, right? Okay. Since A bar is closed, meaning the complement is open. Okay. So you see, so which direction? Maybe this direction. Suppose X is not in A bar. Okay. What is the open set that contain X? Does not intersect A. You just take U equals to X minus A bar. First of all, it is an open set. Second of all, it contains X because X is not in A bar. So it must be in the complement. Otherwise, where is he? Lost, right? It must containing X. And then it does not intersect A. Why it does not intersect A? Why does not intersect A? So you see, here got three things, three claims here. Open set first, containing X, does not intersect A. Okay, we verify the first two. Why does not intersect A? Where is A hiding? In the closure. Remember how we take this closure? So in your mind, you should spell out something here. So you got an X, right? Okay, you got some A. But how you build A bar? You take all the closed set that contains A. And then you take the intersection of them, right? And then you take the complement of it. So really, this A here is hiding inside A bar. So I should write, actually, we have it just now, right? A is in A bar. So X take out A bar is like this. Which way? This way. X take away A is which way? Let me think. Okay. This is true. Okay. So far, okay? Does it make sense? So yeah, that's not intersect A. And a question. What? Any question? No? If A is open, What? Say again. If A is open, A bar is closed, and then? No, X minus A. Wait, no. So I'm trying to argue why this doesn't intersect A, right? So meaning the intersection of so this implies that just another one. So this implies that A intersect X minus A bar is A intersect X minus A bar is empty. Why? Because A is in A bar. You already take out everything in A bar already, but A is in A bar. Yeah. Make sense? You take out a bigger thing, so the smaller thing should disappear, be taken away. Okay. Yeah. Nothing tricky. Conversely is what? If you have all the open set contain which open? Okay. If you have a open set, okay, that contain X does not intersect A, you want to show that it is not in A bar. Okay. If you want to show that it is not containing in A bar, right? What can you do? Sure. So let's write it down. Conversely, since there's this set U containing X, which does not intersect A. Okay. A bar is the intersection of closed set that contains A. Okay. So if you can show that this X is not in one of the closed set that contains A, then you are done, right? So in particular, what closed set you can take here? So 之前 say you can take. We consider the closed set X minus U. Okay. We contain this closed set here. So in particular, this is a closed set, right? Because U is open, so X minus U is closed. And this closed set here contain A. Contain A or not? Why? The U is, there's no intersection between U and, okay, let's write out. There's no intersection between U and A. So let's say this is A, this is U, X is in here. So you take the complement. You should contain A, and it is closed. Okay. So by definition of A bar, the set X minus U must contain A bar, right? Must contain A bar because A bar is the intersection of all the closed set, but this one is one of them. Okay, this is one of them. And then, therefore, X is not in A bar. Okay. Question is, let's go up. Yeah. Is it wrong direction or not? Huh? Correct direction? Correct, right? You see, so A is smaller than A bar, right? Huh? A is smaller than A bar. Okay. So you take away, X take away a bigger thing. X take away a smaller thing. So let me try. Correct or wrong? Did we swap? So let's try. So let's quickly see through a Venn diagram. So let's say we take this A, then we take this A bar. Okay, X takes away A bar as well. Let's just keep this orange with orange. And then X takes away A. This one. Okay, so who is contained with who? So X minus A, X minus, so I think we should stop it. Okay, right. So everything in the orange one is in the blue one. Yeah.
As you can say like A closure of A, you have something that is in closure of A but not inside A. When you take out the set and then you can see why the sign is like that, right?
What do you mean? Yeah. Okay. At first I thought the inclusion should swap. But yeah, we don't have swapping here. Okay. Yeah. Yeah. No. Okay. Any question? Yeah, if not, I think we skip part B. We just skip part B because B will be just pulling out the definition of basis element here. And just pulling out the basis element. So how does basis element react with open set? So if you have a topology that is generated by a basis, means what? For every open set, you can find, so for every open set and every point in the open set, you can find a basis element such that this basis element contain that point and lie inside the open set. Okay, and then this will help you to just check properties on the basis elements. Okay, because basis element will give you that certain inclusion. Okay, now let's finish the definition of Hausdorff and then we will end this class. Are you guys going to the seminar? Yes or no? No. Just asking. I'm not trying to trick you. I'm just asking. No, okay, never mind. Just asking. Okay, so let's start a definition of Hausdorff and then maybe next motivate it. So a topological space X is called Hausdorff space if for every pair, okay, x1 comma y, sorry, x1 comma x2, okay, in X, there exists let's say we put open set first. Tomorrow we will introduce a notion of open interval neighborhood. So there's this open set U1 and U2. where x1 in U1 and x2 in U2 that are destroyed. Okay. So can you imagine what does this Hausdorff space trying to do? If you have 2 points, okay, in your X, you can somehow separate it using 2 open set, okay? If metric space open ball, but in the topological space, we use open set here. Okay. And surprisingly, if the sequence Sn of points in Hausdorff space converge to a point X, then this X is unique. So every Hausdorff space will have a unique limit in the Rn. Okay. So as long as you have Hausdorff space, you will have uniqueness of limit. Tomorrow I will show you if it is not Hausdorff, how can the limit be non-unique? Okay. Yeah. We haven't quite defined convergence and what? Let me see what else. And limit point we haven't introduced, but we'll make it more precise tomorrow. But what I want to say is, whatever happens in your Rn, right, is because of this Hausdorff. I mean, about uniqueness of limit. Okay, tomorrow we will see it. Right, tomorrow we'll see it. You will see that a lot of topological theorem, they will want to include Hausdorffness inside their definition, their property of space. Thursday. Tomorrow is what? Tomorrow is Tuesday. Yeah, Tuesday only got analysis. Thursday. Yeah. All right, we will continue talking about Hausdorff space on Thursday.
S1, S2 must be extreme.
Huh?
S1, S2 must be extreme.
Yeah. Let me see. Yeah, right. You need to mention this thing. So x1, y1 to be different. Otherwise, yeah, you cannot avoid intersection. Yeah.